Next, I would like to present to you closures for the torque. In order to do that, it's good to first give an overview of which different types of torques we have to consider. The first group is the so-called rolling resistance torque. This torque models the impediment of rolling motion due to particle surface roughness. You see it illustrated here. The softness of particles, so the particle is deforming under the normal force, and this then leads to a large contact area between the two particles, or simply the shape of the particles. This causes a contact torque that we need to model, as you will see. The second important type of torque closures is that for torsion. This is a little bit more exotic torque closure, however, it still might be important in some situations. What we here attempt to do is to model the resistance against twisting, essentially, when we move the top particle in this direction and hold the bottom particle in its position. So if you think about the angular momentum balance of one of these particles, there must be a torsion torque at this contact. The work of Luding gives an excellent overview of these two torques. The third type of torques we should consider is the so-called fluid torque. This torque originates from the ambient fluid because, for example, we rotate the particle against the fluid. In contrast to the other two torque types, fluid torque is actually changing the angular momentum of the particle phase. And the reason for this is very simple. Momentum is transferred from the fluid phase to the particle phase. Let us now look into the basics of the rolling resistance. The rolling resistance originates from a misalignment of normal forces. If we consider here a sphere that we load under a normal force Fn, and we're trying to move the sphere to the right, then we're gonna see that the force, the normal force distribution here at the contact here is shifted a little bit to the right here. And this shift of the normal force at the contact here, together with this position of the applied force, gives a torque. And this torque is nothing else than the product of this normal force with this distance d here. So this distance d here is dependent on the softness of the surfaces in contact. It is very often found that this misalignment d depends linearly on the radius of the sphere here. Hence, one can replace the d here with a rolling resistance coefficient mu r here, multiplied with the radius of the sphere. The typical values of this rolling resistance coefficient mu r range from 10 to the power of minus 3, so 0.001, to about 0.4 or 0.5 for a very soft material like loose sand, for example. It is also possible to introduce a rolling resistance force, F roll here, which of course must also induce a tangential force here. There are now two important things to know. First, this rolling resistance torque is analogous to the Coulomb limit. It's the maximum value of this rolling torque that we can experience, and in real life it will depend on how hard we push. So we have to keep this in mind, similar to what we have done for the tangential force. The second note here is that of course one could also introduce such a rolling force here, but this is nothing else as a force double that activates this torque resistance. What we need to do next is to think about the orientation of the rolling resistance torque vector in a more general configuration. Therefore, we consider the collision between a particle I and a particle J that is kind of rolling on this particle I. All this has been very nicely summarized and analyzed by I et al. and I would like to show you just a quick summary of that. First, we have to define a so-called rolling trace UR here. This rolling trace UR is a part of the contact point trace due to this rolling motion. So UR is essentially this contact point trace minus a sliding component. The beautiful thing is now that this DUR, so the incremental change of this rolling trace, is proportional to the relative differential change of the orientation of the two particles. And this is beautiful because this differential change d phi I of each particle is nothing else as a time increment dt times the angular velocity of a particle. So in short, one finds that the rolling resistance must be connected to this relative angular velocity, and this is nothing else as the difference of the angular velocities of the two particles. So this is really good news for us. So with that in mind, we can already continue to the different rolling resistance models. We have to distinguish between different classes. The simplest class is class A, where we have a simply opposing or constant directional torque closure. Again, we use the relative angular velocity omega ij here. This is defined just by the difference of the angular velocities. And we apply the torque simply opposing this relative angular velocity. So you see here, this is the direction, the unit vector of the direction at which we impose this torque, and we always impose the same value. It's simply the normal force multiplied by the rolling resistance coefficient UR and the effective radius Rij. We have talked already about this. This rolling radius Rij is, as already said, identical to the effective radius of the particle collision. Please note that in total analogy to sliding friction, applying this class A rolling resistance closure might lead to a wiggling motion, and the reason for that is that we simply have chosen to apply the torque with the full magnitude opposing the direction. This is not good for slow flow scenarios. Therefore, people have thought about this and came up with a class B rolling resistance model, which is also called a viscous rolling resistance torque closure. And here we don't pick the direction of the torque based on the relative angular velocity, but based on this relative translational velocity of the contact. The drawback of this is that we have to introduce a reference velocity that essentially scales this velocity, because this is now has now the units meter per second, and if we take this torque value, we need to normalize it again by velocity. The second point is that this reduces the wiggling motion significantly. However, this closure is still problematic if we have a slow flow. So the reason for that is that in the quasi-static limit, the angular velocities are very small, and then also this torque is melting away, and we cannot essentially model a quasi-static behavior. So we have to do something else, and this is this elastoplastic spring dashpot model, or in short EPSD model. Here the torque is closed by an elastic component and a viscous component. For the elastic component here, this TRK, we integrate essentially the relative rotation between the particles with time, and similar to Coulomb's law for sliding friction, we use this maximum torque as the limiting case for this torque, for this elastic torque that builds up. So here again, this is simply the integration, the summation of this rolling distance essentially. So we increase the rolling resistance torque by this increment here, and we finally bound it by the maximum value similar to what we do for the Coulomb friction. Please note that we need to keep additional memory because we need to memorize that, we need to integrate that for the next time step. And the beautiful thing is that this closure can have non-zero torque even if the particles are non-moving. And the reason again is if this becomes zero, the torque simply stays as it is. For the viscous component, we do it simply opposing the relative angular velocity, omega ij here. This is nothing surprising, we just apply an additional damping here. Of course, one could keep that also in the case when we exceed the critical maximum torque. However, this is rarely done. With this, I would like to close. See you next time.